Uh, Hi everyone, welcome to the next YugabyteDB Friday Tech Talk for engineers by engineers. I'm Kannan here, happy to join you again this Friday, and I'm accompanied today by Deepthi Srinivasan, another colleague who's going to be covering a very interesting topic today. So over to you, Deepthi. Please introduce yourself, and then you can get right into the topic too.
Yeah. Hi, everyone. Thank you, Kannan, for this opportunity. And it's very nice to speak to all of you today. My name is Deepthi Srinivasan. I'm an employee here at Yugabyte, and I work for the YSQL team. I've been here almost 2 years now. Previous to this, I worked at Nutanix. I worked with their distributed file systems team and later for the object store team. So I've been with distributed systems for like 7 years now. So today I'm just going to get started with the row level geo-partitioning. Are my slides visible?
Yeah, that's right, Deepthi.
Yeah. So today I'm just going to start talking about row level geo-partitioning. So before I start with what row level geo-partitioning is, I'm going to start with why row level geo-partitioning. Then the what becomes clear. So to explain why this feature, I'm just going to start off with this geo-distributed Yugabyte cluster here. It has a node in like 3 regions spread across the world. And let's say now that I create a table in this geo-distributed cluster, right? And let's say I create this cluster, create this table using YSQL with just the default configuration, no fancy settings or anything. So what will happen in the background is that the cluster balancer in YugabyteDB will split this table for me based on the hash of this of the primary key here. So what will end up happening is this table gets split into tablets, and the tablets and its replicas get spread out across the nodes of the cluster evenly by the cluster balancer. Now, because the cluster balancer does this based on the hash of this primary key right here, it's pretty much not in our control what rows end up in what tablets and what tablets end up in what regions and things like that. So what ends up happening when we have like customers all across the world for this geo distributed application is that when they try to access their data, all of the accesses like reads and writes end up going across the world, and cross region accesses like these can be like hundreds of milliseconds in latency. Now now consider like this application could be something like bank transactions or car rental records or things like that. In applications like these, as a database admin or as a user, we actually have some knowledge of the access pattern of the data, if you will. Now, for example, here in this tablet out here, I have a user Alice in US. Now, most probably this record here will be accessed by Alice from somewhere within the US. And similarly, for someone in Europe, if they are accessing any information pertaining to them, we are aware of the fact that most likely it's going to be from somewhere within the Europe. So now, although we do have some knowledge here about about which rows in this table will be accessed by customers in which region, because we just use like the default standard configuration, we could not control how the data was partitioned or where these rows actually went. So this is where row level geo-partitioning comes into play. So here, now given that we have some knowledge about where the rows are going to be accessed, we can use row level geo-partitioning to create some rules on our table. So what we can say is, we'll say that I have this table and I want to partition it based on this column here called region. And I'll tell YugabyteDB that, hey, partition this table such that all the rows in this table with the value US for this region column should go to this separate table here called, let's say, users US. And similarly, all the rows in this table with the value EU for the region column should go into another table, say users EU, with all of the data pertaining to EU. And once we've controlled the partitioning of the table, we can create more rules that say, hey, given this user's US table, please ensure that all of the tablets and all of the replicas of those tablets, like everything, like all data and replicas pertaining to the US users should stay in the T servers of Yugabyte that are in US. And similarly for the Europe table and here for the India table. Now, because we've done this, right? So when the when the users of the application start accessing the data, since we ensured that all the data and all of the replicas are of US up into US and those of Europe are in Europe, we can be sure that all of the accesses end up being local accesses, right? Now, this results in very low latency because now we skip like hundreds of milliseconds of cross-region accesses. The other side effect or another advantage of this configuration is that this helps satisfy data residency requirements like GDPR. For example, GDPR states that the data about European customers should stay in Europe. So now, although you have this table here with data about people from all over the world, you can say that, hey, all the data pertaining to Europe should stay in the nodes in Europe. So in this way, row level geopartitioning helps us really control which users, which set of rows go into which region and how they are accessed. But let's say you have a slightly different type of application, right? Where you don't really need to worry about things like GDPR, but what you want is, say, you want region fault tolerance, but you still want local accesses. Now, in this configuration that I showed here, for example, all of the data of users US is in US, right? Let's say we want region fault tolerance and want the replicas to be spread across the world. Now, to have your cake and eat it too, we have another type of row level geopartitioning as well. So here what we'll do is,
Deepthi,
yeah,
if on your previous slide, we could take a question from the audience.
yeah.
So there was a question, are you hashing on the region now instead of the primary key?
We are not exactly hashing here. So in this configuration, what ends up happening is we explicitly say while partitioning that the rows with value EU go into a separate table. So there's not exactly hashing here. It just says that those with value specifically EU go into table EU. Those with value specifically US go into US. This partitioning method will become clearer when I explain it in the demo. But you can, in this example, I've used this form of explicit partitioning. I would call it list partitioning. You can also partition other types. You can say that a range of values should go into this table. You can still use hash. You can even use an expression on a column to partition the table. There are many types of partitioning. I can go into a little bit detail in that in the demo.
And maybe just one thing I would add is another way to think about it is in this example, we are using the region column to split your data, like this list partition into three child tables, one in Europe, one in India, and one in US. But then each of these child tables could get very, very big. And so the orthogonally, the primary key, like if it's user ID and region coupled, we'll still use hash to then shard these individual large tables into multiple nodes. So these two concepts are kind of complement each other. One is kind of dividing by one dimension, the region dimension, and then once you're divided that way, you still could use a hash sharding strategy based on the primary key because each of these tables can get very big.
Yeah, so yeah, shall I continue?
Yeah, keep going.
So here we have, like I was saying, like if we want to have both the table partitioning with region fault tolerance, then we can do something like this second configuration here. So what we'll do here is, just like in the previous configuration, we'll still say that, hey, split my table into three child tables based on the value of the region column. But this time, instead of controlling the location of all the replicas of your data, we'll only control the location of the leader replica of the tablets in your table. So what this means is that in the previous slide, we said that all of the replicas of the user US table go into US. Instead, now we'll still have one replica in Europe and one replica in India. So we didn't control the location of all of the replicas, but we'll still control the location of the leader replica. So now what is a leader replica, right? The leader replica is the one with the most up-to-date, consistent snapshot of the data. And whenever you perform reads in YugabyteDB, those reads are always served by the leader replica, which has the up-to-date state. So now that we've used our row-level geo-partitioning rules to control the location of the leader replica, what ends up happening is the accesses to the data or the reads end up still being local. But since we have the other replicas spread across the other regions, when you want to do writes or updates, they still end up being cross region. But any accesses or reads that we perform will still end up being local. So I've kind of explained how to visualize row level geopartitioning, if you will. The implementation, I'll get into the implementation part of it when we try to create a table and configure these rules. So we can think of row level geopartitioning as two features. One is table partitioning. So table partitioning is what we used here to say that I have a single partitioned table and split this partition table into three tables based on the value of the region column. So that's all table partitioning. So that helps us explain how we want to split one table into multiple tables. And the second feature that we use is table spaces. So table spaces are used to control the location of the data and all of its replicas. So here, when I said that partition users US should stay in the nodes in the US, or when I said that the leader replica should stay in US. So when I said all of these location based configurations, those are specified using YSQL table spaces. So now to uh, properly show how all of this works, I'm just going to go into a very quick demo. So for this demo, I've chosen a geo distributed cluster here. Actually, let me. Yeah, so this is the geo-distributed cluster that I'm connected to here. I have 9 nodes in my cluster. I have 3 nodes each in India, in Europe, and in US West. And right now I'm connected to 230, which is a node in India. So now that I have my cluster, I'm just going to first create table spaces in this cluster. So I've created 3 table spaces first. So if you can see, I have a EU Central table space, I have US West, I have AP South. And here if you look at the table space configuration, it says that any objects that pertain to this table space will have a replication factor of 3. And these replicas will be placed in cloud AWS, in region EU Central and zone EU Central 1A. These are, if you see, quite simple table spaces. They just say the replication factor and constrain everything to a single zone. But table spaces are quite flexible. We can even create even more complex looking configurations. For example, I'm just going to create a few more table spaces to demonstrate the idea. So here, if you see, I've created a bit more complex table spaces. So here, for example, I've said that any objects pertaining to EU table space will still have replication factor 3. And these 3 replicas here will be spread across these 3 zones: EU Central 1, US West 2A, and AP South 1A. But the leader replica of the data in this table of the tables in this table space will be in EU Central. Similarly, for US table space here, I have again said that data is replicated across all of the 3 zones that I have, but the leader replica stays in US, and so on. For this demo, I'm just going to keep things simple, and I'm going to use the simple table spaces here. But like I've shown here, table spaces are quite flexible. You can create, you can spread your data across any number of replicas. You can control how many replicas go into each zone, and things like that.
And Deepthi, like it might be worth mentioning, that the table space construct itself is has been in Postgres for a while, right? And I think historically it's been used to associate properties like, you might want some tables in SSDs, some tables in hard drives, and you can control the placement of tables in a database differently. And we have extended that concept now to talk not just distinguish between hard drive versus SSDs, but geolocation and where you want the leader for a particular table to be in, and so on.
This is like the cloud native
Cloud
form
native
of the cloud native form of Postgres
table
table
spaces,
spaces.
yeah, and Postgres.
Yeah.
Go for it, yeah.
Yeah. So now I'm going to create the partitioned table. So like the example I was talking about earlier, I have just created a table called bank transactions. And note here that I said partition by list. So I said that this table is a partitioned table, and the column I'm going to use to partition this table is this geo-partition column. Note that this key here can be complex, like you can have multiple columns here. There are many ways to partition the table. For this example here, I'm just using a partition by list. So now that I created the partitioned table, I'm going to go ahead and create the partitions themselves. So I'm creating 3 partitions for this table. So I first have bank transactions EU, and I'm saying that this is a partition of the bank transactions table here. And because this is a partition of this table, it has pretty much the same schema as that of the parent table. And I say that the table space for this partition will be EU central 1 table space that I created here. So this means that bank transactions EU will have 3 replicas, and all of them will be in the T servers that exist in EU Central 1A. And then I said for values in EU. So note that here I said that we partition this table based on the geo partition column, and list partition means that I'll enumerate the values for each partition. So here, this can be a list. So if you had EU here, maybe if this could have been like a country column, and you could have had France, Europe, Germany, like this could have been a list basically. And for this example, I've just chosen a list with size 1. So I've said that, hey, when you insert any data into bank transactions table, and if the row has value EU for this geo partition column, please route that row into bank transactions EU. And similarly for bank transactions India, and similarly for bank transactions US. So if you notice, India went into AP South, US went into US West 2 table space. So now that I created the partitions, I'm also going to go ahead and create indexes for them. So note here that I'm creating an index for every partition, and also I'm making sure that the index has the same table space as that of the indexed table, so that the index and the table are situated in the same region. So as I wait for the indexes to get created, I'm just going to quickly show how the cluster looks like. So this is the, oops. So I'm just going to go ahead into the UI for the cluster to actually show how the placement looks like. So I'm just going to go into the master leaders UI, and here I have, here you can see here the list of all the tables that I just created right now. So let me just go into bank transactions EU. So if you see here, bank transactions EU has this replication info here that says that pretty much matches what we think, right? All of the replicas are in AWS EU Central 1A. Now, if you look at all of the tablets of this table, so if you see here, for each tablet, all of the replicas are in the same set of 3 nodes, like 94, 109, and 161. So if you just take, mine is a 9-node cluster, right? But if you see here, all of the tablets are placed in the same 3 nodes. And let's take a look at 94, 109, and 161 here in my list. So you can find them here. They are all they are all T servers that are in EU Central 1A. So basically, you can use the master UI to verify if you wish to, like, to see if all your placement and configurations look correct. So so we see here that my partitions are ready, my indexes are ready, and when I try to describe my partitioned table, I can see that it has like 3 partitions. Um, it has 3 partitions. So now I'm going to go ahead and start inserting data into the partitioned table. So if you see here, I've inserted. Oh, did I switch off timing here? Okay, that's fine. So I've inserted. So I've inserted data into. I've inserted 2 rows into every partition. I have 2 rows in EU. I have 2 rows in India. I have 2 rows in US. Right? So let's check out the table state now. So here, if you see this, I've done a select star on the partitioned table, and here you can see that all of the rows with value EU are actually in the bank transactions EU table. All of the rows with value India are actually in bank transactions India, and the ones in US are in bank transactions US, right? So since my timing was off earlier, let me just try something. So
are you planning to insert rows with a few more different account numbers?
Yeah. So I have a primary key, so I have to use something different here. So let me just.
And do you have a unique index on the account ID, or it's a non-unique? Okay, that's fine.
Yeah. So here, if you see something, I inserted something into EU, and conversely, let me try to insert something into India. So let's do this. So note the high difference in latency. Like, so this one here went into, I'm connected to a node in India, like I said before. And if you see here, this one here is actually a global transaction, because this, when I inserted values into bank transactions EU, I actually modified bank transactions EU and the index on bank transactions EU. And because this is in Europe and my node is in India, this took up like nearly 400 milliseconds. But when I did the same thing for the India node, so this becomes what we call a local transaction, because I ended up inserting values into bank transactions India, which is in the local region, and the index on bank transaction India, which is also local. And look at the vast difference in latency between the two. So it's in our best interest to try to keep our transactions local because of this vast difference in latency. Like, I can also show another example of a global transaction. So what I'm going
in this case, maybe it's worth calling out that the main thing, like at least by data model design, the design is correct, meaning the index and the table are both within the same region, right? So data model design wise, it's an optimal design, right? Because even your EU transactions table, its index is in the EU table space. Maybe
Yes.
here the real reason for the higher latency is because you're connected to a different region and not the ideal region for this particular partition, right? But in the real world, the 99 percentile case is like, you're accesses to EU rows will be coming when you're connected to EU set of servers in Yugabyte and say maybe India servers in the other case. So you shouldn't have this as the common case. Yeah, so it's more like, which servers are you connected to initiate the work is causing the difference, right? But it's a good design for the data model as it stands.
Right. So like I was explaining, to reiterate, like I was explaining before, most likely this EU insertion mostly came from a customer in EU. So what would have ideally happened is this insert would have happened from a node connected to EU. From there, we would have had a single digit latency here. I was just trying to explain like the difference, the distance between regions causes.
Yeah, makes sense.
So yeah, so here I have another example of a global transaction, if you will. So here I'm running an update. So what I've done here is I had this user ID 200 here, and this was in the local table in India. And I said, set the geo-partition column value to EU. So in the background, what actually happened was uh, we actually deleted this value from the table bank transactions India, and we inserted that value into bank transactions EU. So if you take a look at it now, so this is actually a transaction spanning both global and local tables, right? And this again ends up being this ends up again being a high latency query, right? So yeah, so here
Yeah,
we
I mean,
can see. Yeah.
this is pretty cool. Basically, I mean, the fact that transactions can span different child partitions. Yes, of course, the latency will be higher, but the functionality just works. Your ability to move the geo home of a particular row by a simple looking update statement, and magically all of this happens in an atomic acid compliant manner is cool.
Yeah, so we can see here in the output that that's precisely what happened. Our user ID 200 is now in the bank transactions EU. So in the background, we modified like 4 tables, the India table and index and the EU table and index, and all of this happened in a single transaction. And yeah, so that's pretty much what happened behind the scenes in this update. So
and there's one question coming, Deepthi, which is like, what happens if the record you're inserting has a geo-partition column or a region name which is you're not listed? Like if you were to type some other geo-partition value, what would happen?
So that would actually result in an error. So we have to use either EU, India, or US here to insert into this table. But the table partitioning structure is quite flexible. You can add new partitions anytime. Also, the another thing that I would state is you can create something called a default partition. So you would create here one more. So if we looked at this create statement here, you would say, oh, create table bank default, and you, instead of this for values here, you would just say default. So
Yeah.
what that means is if you inserted any value here that is not EU, India, or US, they would all be routed to that default partition. So we could do even that.
Yeah, that makes sense. Thank you.
So now I'm going to start talking about one of the most common looking queries that we will see in such applications. So I'm just looking up some user ID, right? And here, if you see, like I already said, we expect that most of our accesses will be to the local region. And here I am looking up a row in India. But if you see, this took up like hundreds of milliseconds, right? So if we took a look at the plan from the YSQL planner. So it went through all of the partitions of the partition table, and it tried to find out the user ID 500. And that's why we have such a high latency here, because we are looking at partitions across all of the regions in the world. Now, here, like I said, we already know the access pattern of the data. So what if we did something like this instead? So then here we can see that I took a risk and I said that I know that my geo partition is in India. So I added a where clause here that said, hey, just look at my India partition. And then the planner was able to look at this where clause restriction and figure out that it only needed to look at the single partition in India, right? And so that's why we ended up having like a single digit latency in here. But now that even if I want to use this knowledge, right, like, okay, all my accesses are local, if you were to write the same application, then if your application server is in US and is connected to a UST server, it should know to add geopartition US, and it should know to use, say, geopartition EU. Now this can quickly turn extremely cumbersome, because now we are going to expect the application server to know where it's running and what is the appropriate value you used for the geopartition column, and so on. So this can increase application complexity pretty quickly. Now, to make things easier, we have this uh, YSQL has a function called YB is local table. So what this function does is it returns whether a given table is in the local is attached to a table space that pertains to the local region or not. So if you take a look at this table OID column right here, so the table OID, it's a system column that's present in all tables, states which table the rows belong to. So for example, if you take a look at all of these EU rows here, they all belong to a table with ID 16942. Similarly for India and similarly for US. And what this function does is it looks at this table and figures out whether this table is indeed local or not. And that's what happened here, because because I'm connected to a node in India. What ended up happening is the planner knew that I only want local rows, and it was able to look at only the local partition. So I also have a node here in EU. So let me try running this is a different node here, 94, which is in EU. So if we use the same function connected to EU node, then we can see that now we are only looking at the EU partition. So this function can easily be used to look up only the local partition of your data wherever your application is. So this means that you can pretty much do some cool things like this. Like for example, say if I wasn't exactly sure which location my user ID is, then I can easily write a query like this that first looks up the local partition. If my row is in the local partition, it'll return the row from the local partition, and if not, it looks at all of the other partitions. So if you see here, although I did write a query that maybe if you didn't analyze it too much, it looks like it looks at the entire bank transactions table, but in reality, if you see, the time is just 1 millisecond. So which means that it found the row I needed in the local table, and it returned. Like we can use the same for, um, like for example, if I was now looking up a user ID that's not in the local table, we'd have ended up having this 100 millisecond latency here. So the YB is local table is a pretty useful function that's going to help us look up the local partition. Now, there are actually many more features and things that are present in table partitioning, like in row level geopartitioning, mainly because it's a combination of a big feature called table partitioning and another pretty flexible and huge feature called table spaces. So all of the features that you use, or all of the functionalities that come with them, can also be used in row level geopartitioning. Like I was saying, we can add partitions anytime, we can detach partitions, we can drop partitions, and every child partition here, like bank transactions US, bank transactions India, they are basically regular tables. So you can create triggers, foreign key relationships, like all of the things that you create on regular tables can be done on them. So not going to go into too much detail on the intricacies of them in respect of time. And also we've had previous YFTT episodes focusing on table partitioning, and there was one by Frank on table spaces. So I'm going to stop the demo right here. And I just wanted to bring to attention a couple other things. We have this GitHub ticket here that tracks the entire feature of row level geopartitioning. This shows all of the features that have already been implemented, some of the features that we are planning to implement. We have one that will come in soon, called per region backup. So you can say things like all the tables in US should be backed up to a S3 bucket in US. All of the tables in Europe should be backed up to a S3 bucket in Europe. That reduces the latency of backups, right? So things like that. We also have another really cool functionality coming up. This is to add a set of new functions here called YB server region, zone, and cloud. So this YB server region returns the name of the region to which we are connected to. So then you could easily create a partition table like this. So here I have a geo-partition column here. And here I said the default value is YB server region. So since like Kannan was explaining earlier, we expect that the inserts to the table are from the local region. So that being the case, if you are in EU, you want to run an insert, you no longer need to specify a value for that geo partition column. It will automatically be populated here, EU Central 1, because we said the default value for this column is the local region. So when this comes in really handy when you're trying to port an existing application to use row level geo partitioning. This really means that we don't have to change the values of the we don't have to change the structure of the insert queries anymore. So yeah, so this parent ticket here tracks a lot of the further enhancements we are planning, and it's a good place to request for any new things here, any things that make things easier. So that's this part. With this, I'm going to just conclude my presentation with saying that row level geopartitioning is a feature that really helps us control how helps us to control at a row level how our data needs to be placed and how it needs to be accessed. And this is a really important feature along with follower reads, synchronous replication, asynchronous replication. So pretty much YugabyteDB gives you a lot of things to choose from if you want to have a good multi-region deployment.
Yeah, thanks a lot, Deepthi. Maybe like just an example I might say is like, suppose you're building a shopping cart like application. The shopping carts have a certain access pattern. They get created, and then you add items into your shopping cart when you're making your purchase, and then it goes through the checkout microservice and so on. But typically the longevity of a shopping cart may be even less than a day. And during that time, a lot of that users interaction is likely to be coming from one data center. So in the common case, starting by inserting a row for that shopping cart in a geo-affinitized manner, and then making changes to it, like adding items into it, all of them, you can have an optimal performance while still getting geo replication and all that, but by controlling exactly the placement of where the replicas are or where the leader tablet for that replica is, while still supporting the case that if for some reason there's a failure event, if that entire region is down, I can still access that cart from a different data center, although with a slightly higher latency, right? So you kind of have an active system, which in the healthy case is really performing with very low latency, but can still handle the failure cases. So I think this is a feature we're quite excited about. I think there was one more question that's coming in, again to do with let me just read that question out. What happens if you specify a default clause on a different partition? Does it move the default partition or error out? I didn't quite understand the question, but Deepthi, if you did.
Does it do you want to create two default partitions? Is that what it is? If that is the case, no, we can only really have one default partition. If you want to change it, then we don't have an easy way to do it. You would have to detach the default partition, add a new default partition, and then move values from here to there. So
yeah,
that's the only long-winded way we have at the moment.
Yeah, and maybe I would just probably summarize your earlier answer again, like to a similar question earlier, that fundamentally, like if you had a geo partition list value which you had not already specified in your partitions, then that case will error out. But then if you want to handle such an omission, then you use the default handling as your syntax sugar to say, hey, if it is not one of these three values, everything else goes in this partition number 4. And between those two constructs, you can pick which one you prefer. Do you prefer the erroring semantics, or do you want to have a default handler? So I think it's kind of a flexible model. But if we misunderstood your question, please don't hesitate to post in the YB users Slack channel.
Yeah, and if the question was if the default partition can be moved, in the sense that can we change the table space of the default partition? Yes, we can. We have a beta feature that allows you to alter the table space for a table. So if that was the question, then yes, you can change the table space of the default partition.
Okay, I think we are a little past time, but really wanted to thank everybody that joined us, and please join us again next week on another interesting topic. And Deepthi, over to you for comments.
Yeah, thanks everyone for listening. It was great to talk about the feature. Like I've already shown the parent ticket that we have for O-level geo-partitioning. So any further enhancements you think is important, please feel free to add a comment over there. And if you have any more questions, I think please uh, please ask us on community Slack. You can even reach out to me on LinkedIn. Yeah, please just let us know any suggestions, any questions that you have.
Thank you.